Imagine for a second that you're just, sitting at your kitchen table.
Right.
And your phone buzzes. So an AI that is running entirely locally right on that device, has just quietly finished scraping your deeply personal financial records.
Okay, wow.
Yeah, and it formulated this highly aggressive negotiation strategy, and it silently secured a lower mortgage rate for you.
By arguing with the bank.
Exactly, by literally arguing with a massive banking AI in the cloud. And it did all of this with zero corporate safety guardrails, no monthly API subscription fees, and complete impenetrable privacy.
It sounds totally ridiculous, I know.
Right. It sounds like a pitch for some sci-fi movie, but
Yeah.
that is the actual tangible reality of the 2026 AI landscape that we're looking at today.
Yeah, and it is a radical departure from where we were, even just 2 years ago. The whole industry is experiencing this profound fracture.
A total shift.
Exactly. The era of simply, renting intelligence by calling a cloud API is breaking apart, and it's giving way to this new ecosystem where you actually own the intelligence right on your own silicon.
Okay, let's unpack this. Because if you look at the history of computing, this pattern is incredibly familiar.
It really is.
Think about the 1960s and 70s, right? Computing meant mainframes, giant monolithic climate-controlled rooms.
Oh yeah, the size of a whole floor.
Exactly. You had to submit a physical punch card to a technician behind glass, and maybe, just maybe, you got your answer back the next day.
If you were lucky.
Right. It was centralized, it was heavily guarded, and it was entirely out of your personal control. And honestly, for the last few years, AI has basically been a mainframe model.
That's a really good point.
You send your prompt off into the ether, it goes to some massive server farm owned by a massive tech giant, and it sends you an answer back.
Well, provided your prompt doesn't violate their endless terms of service.
Provided you follow the rules, exactly. But then the 1980s happened. The microcomputer revolution.
The personal computer.
Yes. You suddenly had this beige box sitting on your desk. It wasn't as powerful as the mainframe, but it was yours.
You owned it.
You could take it apart, you could hack it, and you could run whatever software you wanted without asking anyone for permission. And today, our mission for this deep dive is to map out this exact same transition, but for artificial intelligence.
And we have a massive stack of sources to go through today to do that. We're pulling from early 2026 technical documentation, sprawling Reddit threads from developers actually in the trenches.
The people building this stuff.
Right. Plus enterprise cost analyses from hardware vendors and open source model rankings. We're synthesizing all of this into a cohesive roadmap.
Because we're looking at a massive, undeniable shift toward digital sovereignty.
Digital sovereignty, yes.
Running incredibly powerful, completely uncensored models right on your local hardware, whether that's a literal server rack you own or just the smartphone in your pocket.
And securely connecting those models to your own private data.
Right. And what's fascinating here is that we aren't just examining a technological pivot.
Not at all.
If we connect this to the bigger picture, we're tracking massive shifts in enterprise economics. We're talking legal liabilities of data routing.
Oh, the legal side is huge.
And quite literally, the mathematical definition of morality that's being encoded into these systems.
Which is just wild to think about. But to really get why a local model on your phone is suddenly so devastatingly capable today, we kind of have to contextualize the sheer, almost absurd scale of the journey from 2018 to early 2026.
Yeah, because if you aren't tracking the numbers day by day, the scale is honestly incomprehensible.
It really is. Let's look at our historical Wikipedia data on large language models for a second.
Okay, lay it on me.
So, rewind to June 2018. OpenAI releases GPT-1.
The granddaddy.
Right. And at the time, it was an absolute breakthrough. Do you remember how many parameters it had?
I think it was something like 117 million.
Exactly. 117 million parameters. Now, jump to the data we have for early 2026. We are tracking frontier models like Kimi K2.5 from Moonshot AI.
Right.
The parameter count for that model is 1,040 billion.
Wait, so 1.04 trillion.
Yes. 1.04 trillion parameters. And Xiaomi's MiMo V2.5 Pro sits at 1.02 trillion parameters.
That is insane. From 117 million to over a trillion in under 8 years.
It's exponential growth on steroids. And those parameters require a staggering amount of training data to actually become intelligent.
Right, because an empty brain isn't helpful.
Exactly. So that MiMo V2.5 Pro model, it was trained on 48 trillion tokens.
48 trillion.
Yeah. And to put that into a physical perspective for you, a trillion tokens is roughly equivalent to a few million full-length books.
Oh, wow.
The industry has effectively compressed a vast swath of human knowledge into these massive neural networks.
Okay, but I have to challenge the physics of this for a second.
Go for it.
If we are building these trillion-parameter behemoths, the math for power consumption simply does not work.
You're not wrong.
I mean, if every time I ask a cloud AI to, summarize a 3-sentence email, it has to fire up over 1 trillion parameters, the electricity draw would be catastrophic.
We need a dedicated nuclear reactor for every data center just to handle daily office tasks.
Exactly. How did the industry not hit a hard physical wall with that?
Well, the funny thing is, they did hit a wall.
Oh, really?
Yeah. Around 2024, the dense scaling laws, where every single parameter fires for every single prompt, became computationally unsustainable. It's just cost too much money and power.
That makes total sense.
So the solution to that bottleneck is actually the bedrock of 2026 AI efficiency. It's an architecture called MOE.
Mixture of expert.
Exactly. Mixture of experts.
Okay, so walk us through the mechanics of that. How does an MOE actually bypass that physical bottleneck?
Think of a traditional dense neural network as a generalist. When you send it a prompt, the entire model activates.
The whole thing turns on.
Right. The math requires data to pass through every single weight and bias in the entire network. That is incredibly computationally expensive.
Yeah, that sounds like a nightmare for the servers.
It is. So mixture of experts completely rewrites that pipeline. It turns the neural network into a sparse architecture.
Sparse meaning?
Empty. Sparse, meaning it only uses what it needs. Let's look at a model from our 2026 data, Sarvam 105B.
Okay, I have the notes on that one. This is India's first independently trained foundation model.
Yes. So it possesses 105 billion parameters in total, but it utilizes only 10.3 billion active parameters during inference.
Wait, really? So it holds a knowledge of a massive 105 billion parameter model, but it runs with the energy footprint of a much, much smaller one.
Precisely. The architecture introduces something called a gating network. Some people call it a router.
A router, like for Wi-Fi?
Similar concept, yeah. The model acts as this massive committee of highly specialized subnetworks. Those are the experts.
Ah, okay.
So when you submit a prompt, the routing algorithm analyzes each individual token and mathematically calculates which specific experts are best equipped to handle it.
So it's basically directing traffic.
Exactly. It might say, this token involves Python syntax, routed to expert 4. This token involves database structuring, routed to expert 12.
And the rest of the model?
The vast majority of the network remains completely dormant. It doesn't draw power. You access a massive reservoir of latent knowledge, but you only pay the compute cost for the specific pathways that are actually activated.
Okay, that makes perfect sense. It's kind of like walking into a massive university library, right?
That's a good analogy.
Like, you don't ask every single professor in the entire building to help you solve a calculus problem.
Look, that would be chaos.
You walk past the literature department, you walk past the history department, and you just knock on the door of the math department.
That is a highly accurate way to visualize it. And this sparse routing is ubiquitous in 2026.
Everyone is using it.
Everyone. Xiaomi's MIMO V2.5 Pro is over 1 trillion parameters, like we said. But its MOE architecture means it only activates about 43 billion parameters for a given pass.
That is a massive reduction.
Huge. That architectural leap is literally the only reason the global power grid hasn't buckled under the weight of AI inference.
Wow. And the leap isn't just in how they manage their physical size either. Our sources point to a massive shift away from simple pattern recognition toward what they're calling agentic reasoning.
Yes, and this is the qualitative leap that separates the models of 2026 from everything that came before.
How so?
Historically, LLMs were basically hyper-sophisticated autocomplete engines. They just mapped the probability of the next most likely token based on their training data.
Right, just guessing the next word.
Exactly.
Yeah.
But models like OpenAI's O-series, the O1, O3, and O4 Mini and DeepSeek V3.1, they operate on a completely different paradigm.
They actually think.
Yes. They possess a distinct thinking mode, utilizing techniques rooted in Monte Carlo research.
Okay, but what is actually happening under the hood when a model enters that thinking mode? Because from a user perspective, it just looks like a loading spinner for 10 seconds before the answer magically appears.
That's the illusion, yeah. Under the hood, the model is generating hidden chain-of-thought tokens that you never actually see on your screen.
Hidden tokens.
Right. Instead of immediately guessing the final answer, it dedicates actual computational power to the process of problem-solving at runtime.
So it's working it out like scratchpad math.
Exactly. It breaks the prompt into subtasks. It explores branch A, evaluates its own logic, realizes branch A leads to a dead end, prunes that branch, backs up, and explores branch B.
It's simulating an internal dialogue.
Yes, it's verifying its own mathematical or logical steps before it commits to outputting a single word to you.
Which perfectly explains the capabilities of that Kimi K2.5 model we mentioned. Our notes highlight its agent swarm technology.
Oh, the swarm tech is incredible.
Yeah, it says here it can coordinate up to 100 parallel subagents.
All at the same time.
Right, so if you give it a massive software engineering task, it doesn't just try to write the code linearly from top to bottom, it spins up an overarching project manager agent.
A virtual boss.
Yeah, and that manager spins up 50 coder agents to tackle different modules, and maybe 20 testing agents to run diagnostics on the code as it's written, and 10 debugging agents to fix the errors that the testers find.
All running concurrently, all talking to each other.
That is just wild. It forces us to stop treating the AI as a single conversational chatbot and start treating it as a dynamic, highly scalable virtual workforce.
And the combination of mixture of experts keeping the compute costs low and agentic reasoning enabling that complex task orchestration, it creates an incredibly potent cloud ecosystem.
Okay, so we've established that these frontier cloud models are unimaginably massive and complex.
Giant mainframes.
Right. But here's the paradox. The counter-movement to these trillion-parameter leviathans is arguably having a much deeper, more immediate impact on how you and I actually work day to day.
The push for local.
Yes. The industry has figured out how to distill that massive intelligence down into small language models, or SLMs, that fit entirely on an edge device.
And the SLM revolution is the catalyst for true digital sovereignty. Because owning your intelligence is completely impossible if that intelligence requires a $100 million data center just to execute.
Exactly. But we should define our terms clearly here because scale is relative, right? I mean, in 2018, 117 million parameters was a massive breakthrough.
Right.
But our Bentamel source data for 2026 defines SLMs typically in the sub 1 billion to 10 billion parameter range.
Yeah, the classification of an SLM today isn't just about a rigid parameter count. It's really defined by deployability.
Where it can run.
Exactly. An SLM is engineered specifically to run reliably within highly constrained environments. You don't need a server farm. You can run it locally on a standard laptop or, more critically, on a current flagship smartphone.
Like running on a Snapdragon 8 Gen 3 or an Apple A17 chip.
Precisely.
Right in your pocket.
But logically, you have to sacrifice something, don't you? I mean, if you shrink a neural network from a trillion connections down to 3 billion, doesn't the intelligence just collapse?
You would think so. Like, if I ask a 3 billion parameter model to write a Python script or perform logical deduction, isn't it just going to hallucinate terribly because it doesn't have the capacity?
Well, that was the assumption for years.
Right.
And previously, it was totally accurate. Small models that were trained from scratch on raw web data were highly prone to hallucination and logical failure. They were basically toys.
Right.
But the science of training has evolved to bypass that problem entirely. Today, small models achieve their capabilities primarily through 3 really sophisticated pipelines.
Okay, what are they?
Distillation, high-quality synthetic training data, and post-training reinforcement learning.
Okay, distillation. Like concentrating a liquid to get the purest essence of it.
The conceptual framework is actually very similar. In AI distillation, developers don't force the small model to learn everything from scratch like a toddler.
Okay.
They use a massive trillion-parameter frontier model as a teacher.
So the big model teaches the small one.
Exactly. The teacher model is prompted to generate incredibly complex reasoning traces, detailed code explanations, and step-by-step logical deductions. And then the small student model is trained directly on the high-quality outputs of the teacher.
So in mathematical terms, they align the probability distributions.
You're effectively transferring the reasoning behaviors and the instruction-following capabilities of the massive behemoth directly into the compact architecture of the SLM.
So it's basically, instead of a novice trying to learn chess by staring at a million random games played by amateurs,
Right.
the novice just studies the exact perfectly annotated moves of a grandmaster.
That perfectly illustrates the efficiency game.
Yeah.
The large model already did all the heavy lifting of figuring out how logic works, and it just hands the small model the final blueprint.
Yeah. Okay, that makes sense.
And that leads directly to the second pipeline. Synthetic data. Microsoft really pioneered this approach with their Phi series of models.
Right, because historically, models were fed just massive, noisy data sets, unverified web pages, random toxic forum arguments.
The signal-to-noise ratio was terrible. It was a mess. But Microsoft inverted that. They used large frontier models to generate millions of highly structured, reasoning-dense textbooks and targeted exercises.
Wait, they had AI write textbooks for other AIs.
Exactly. And when you train a small model exclusively on this incredibly high-signal synthetic data, it punches vastly above its weight class.
Because its foundational knowledge isn't cluttered with internet noise and garbage.
Precisely. It learns pure logic.
Let's actually weave this into the 2026 SLM All-Stars we're tracking from Bentamel, because this shows exactly how these models are being used.
Yes. Let's look at the actual models.
So if you're building a global product that needs to run on a variety of edge devices, maybe a lightweight assistant that needs to see the real world, you don't have the luxury of a massive compute budget.
You really don't.
That's where a model like Alibaba's Qwen 3.50.8b comes into play. It is tiny. It's only 0.8 billion parameters.
Yeah.
But it's fundamentally multimodal.
Which is an engineering marvel at that scale, frankly. Packing a highly functional vision encoder alongside text processing in under 1 billion parameters allows for incredible utility.
So it can process text, images, and video natively.
Yes. For an application running locally on a phone, where a user might point their camera at a document or ask a question about a short video clip, it executes flawlessly without ever pinging a cloud server.
And our notes say it boasts a 262,000 token context window.
That's the crazy part. It can process entire books or massive code bases locally while supporting over 200 languages at 0.8 billion parameters.
That is just wild. But then you have the battery drain problem on mobile devices, right?
Always a bottleneck.
Google DeepMind tackled this with Llama 3N E2B IT.
Yes, and this is built on a miniature version of the mixture of experts architecture we discussed earlier.
Okay, so MOE, but for phones.
Exactly. Google refers to it as selective parameter activation. The model contains roughly 5 billion parameters of knowledge, but it only activates the equivalent of a 2 billion parameter model during inference.
So it saves massive amounts of battery.
Right. And it natively accepts text, image, audio, and video inputs. It provides all the multimodal capabilities required for modern on-device apps like real-time voice translation or visual search.
All while meticulously managing the thermal load and battery life of the smartphone so it doesn't melt in your hand.
Exactly. But if you need raw analytical brain power over multimodal features, that's where the synthetic data approach we talked about really shines.
Oh, right. Microsoft's 5.4 mini instruct.
Yes.
That one sits at 3.8 billion parameters, but our data shows it routinely rivals much older 7B and 9B models in raw logical reasoning and coding tasks.
It does. The trade-off, however, is deeply tied to its size. Because it is highly compact and trained heavily on synthetic reasoning data, those AI textbooks, it lacks broad encyclopedic world knowledge.
Oh, I see.
It will solve a complex logic puzzle flawlessly, but it might hallucinate wildly if you ask it for the biography of a niche historical figure.
So it has the logic engine of a mathematical prodigy, but the general trivia knowledge of an isolated hermit.
That is a very accurate description, which necessitates pairing it with external data sources in production, a concept we will absolutely unpack when we discuss our RIC later on.
Definitely. But looking at the final notable model on the Bentamel list, Hugging Face's small LM33B, we see another critical feature for local deployment.
Total transparency and user control.
Right. They open sourced the entire blueprint, the data mixture, the training pipeline, literally everything.
And from a user standpoint, it features dual mode reasoning.
Yeah, this is cool. You can explicitly send a /think command or a /nothink command.
You are in total control of the latency.
Right. You default to fast, immediate responses for simple queries, and you only pay the time penalty of deep reasoning when you actually need it to solve a hard problem.
So summarizing this landscape, these SLMs are not compromises. They aren't just worse versions of cloud models.
They are highly specialized surgical tools.
Exactly. The 2026 workflow involves utilizing a massive 1 trillion parameter cloud model for macro-level architectural design or deep strategic planning.
The heavy lifting.
Right. But your daily, hour-by-hour automation drafting emails, summarizing local documents, translating live audio, that is executed by a 3 billion parameter SLM running natively, fast, and completely privately on your device.
Which brings us perfectly to the brutal economic and legal reality for the enterprise sector.
And this is where things get really serious.
Yeah, because if these SLMs and local servers are so highly capable, why do companies still default to cloud APIs?
Because it's frictionless.
Exactly. It's easy. You grab an API key, you paste it into your code base, and suddenly your application has intelligence.
Magic.
But as AI moves from just being a fun prototype feature to deeply integrated enterprise operations that touch highly sensitive data, That frictionless API call is turning into a massive financial and legal liability.
Let's look at the actual cost of cloud compute in 2026 because the numbers are staggering.
Yeah, we have granular data from VRLA Tech. They're a hardware vendor specializing in custom AI workstations and local servers.
And to be objective, cloud prices have seen significant compression over the years.
They have. In 2023, renting a single NVIDIA H100 GPU instance cost upwards of $7 an hour.
Very expensive.
But by early 2026, depending on the provider, that has compressed to roughly $2.50 an hour.
Which sounds incredibly affordable on paper.
Sure, for an hour.
Yeah.
But VRLA Tech breaks down the math for a real production environment. You aren't running a single GPU for an enterprise application.
Never. You need multiple GPUs just to handle concurrent user requests without massive latency.
Right. So if you spin up a standard 4-GPU H100 setup in the cloud, running 247 at $2.50 an hour, that calculates to roughly $70,080 a year.
Just burning cash.
Yeah, and over a 4-year hardware lifecycle, you are paying over $280,000 in rental fees.
And at the end of those 4 years, what do you own?
Absolutely nothing. You have zero capital assets. You just rented a computer for $250,000.
And this economic reality is driving the massive surge in on-premise hardware acquisition.
The shift back to owning your own servers.
Yes. VRLA Tech highlights their 2U LLM server architecture. This is a physical piece of hardware you install in your own server rack, configured with 4 NVIDIA RTX Piro 6000 Blackwell GPUs.
Okay, and that provides 384 gigabytes of combined video RAM, right?
Exactly, which is more than enough VRAM to run highly capable 70 billion parameter open weights models natively with zero cloud dependency.
Completely offline.
Right. And the return on investment metric is staggering. Against that $70,000 annual cloud burn rate, a physical server of this caliber hits the break-even point in just 4 to 8 weeks.
Wait, 4 to 8 weeks?
Depending on exact utilization rates, yes.
That is absurd.
For enterprise CTOs in 2026, the performance metric has completely shifted from tokens per second to tokens per dollar.
That makes total sense. If you are serving continuous inference to thousands of employees or app users, paying a meter rate per API call is financially ruinous compared to the fixed cost of local hardware.
It just doesn't scale.
Okay, here's where it gets really interesting, though. The financial argument is compelling, but the legal argument is practically existential.
Oh, the legal side is terrifying for companies right now.
Looking at the risk analysis data from Wednesday Solutions, their 2026 report reveals that 43% of U.S. enterprises are entirely unaware that default usage of standard cloud AI APIs may include data training rights.
43%. That statistic represents a massive systemic vulnerability.
It's a ticking time bomb.
It is. While providers often state that API data is exempt from training by default, or they offer opt-out mechanisms, terms of service are fluid.
They change them all the time.
Exactly. For highly regulated industries, an opt-out policy hidden in a PDF is not a durable contractual guarantee.
Let's trace the actual mechanism of data transmission here, just to make it real for you. Imagine you are building a healthcare application.
Okay.
A user types their specific medical symptoms into your app interface. If your app routes that query to a standard cloud API to generate a summary,
Which is how most apps work.
right, you have just transmitted protected health information PHI across the open internet to a third-party server.
And if you execute that transmission without a rigorous business associate agreement, a BAA, firmly in place,
You trigger an immediate HIPAA violation.
the liability exposure is massive. And this compliance friction applies across all sectors.
It's not just healthcare.
No. If a financial services app routes customer transaction histories to a cloud API, it triggers deep complications for SOC2 audits.
Right.
If an application serves European citizens, transmitting their data to a US-based AI infrastructure requires navigating a massive labyrinth of GDPR assessments.
It's a legal minefield.
And even if an enterprise successfully negotiates a secure private cloud contract, they remain entirely beholden to that provider's uptime, their latency spikes, and their internal content filtering protocols.
Which is exactly why Wednesday Solutions points to the definitive 2026 enterprise architecture. Route the sensitive data to the edge.
Keep it local.
Yes, if the patient's medical query never leaves the physical smartphone, you cleanly bypass the entire category of third-party transmission risk.
It's brilliant. You utilize a local, specialized SLM to analyze the PHI natively on the device.
And you only invoke the expensive generalized cloud APIs for anonymized complex reasoning tasks where no personal data is attached.
Digital sovereignty is no longer just a philosophy for hardware enthusiasts. It is a strict legal framework for corporate survival.
It really is. However, once you transition the computation to your local hardware to secure your data, you unlock a highly controversial secondary capability.
The morality question.
Yeah, by owning the model, you gain absolute sovereignty over its internal moral compass. We have to examine the frontier of uncensored AI.
This is where the tech hits philosophy.
So to understand this, we need to look at how frontier models are constructed. When major corporations train an AI, they invest massive resources into a process called alignment.
Heavily utilizing techniques like reinforcement learning from human feedback, or RLHF.
Right. They mathematically condition the neural network. They tell it. If a user prompts you for instructions on synthesizing illegal compounds, refuse the prompt. If a user asks for hate speech, refuse.
If a user prompts you to analyze the code of a known computer virus, refuse.
Right. And that is exactly where the friction lies. This standard safety alignment frequently produces what developers call refusal bias.
The model becomes overly conservative.
Extremely. If you ask an aligned model to generate a dark, dystopian sci-fi narrative, it will often refuse or pivot into a lecture on positive conflict resolution.
Which ruins the story.
Totally ruins it. Or if a cybersecurity professional asks it to deconstruct a piece of malware to understand an attack vector, it flags the prompt as malicious and refuses to execute the task.
Which hinders actual security work. So uncensored models have had these safety alignment layers meticulously extracted.
They are stripped out.
Right, they operate with aggressive obedience. They will faithfully execute the prompt provided by the user without encountering internal moral friction or imposing corporate safety guidelines.
Now, looking at the data impartially, this presents a massive duality.
It does.
Removing the guardrails allows for absolute, unrestricted intellectual inquiry, and it removes corporate bias. But conversely, it shifts the burden of safety entirely onto the individual user.
Because an uncensored model will absolutely generate harmful, dangerous, or highly explicit content if explicitly directed to do so. It won't tell you no.
Right. The open source community, particularly as tracked in the Decode's future reports, argues for this capability as a fundamental digital right.
Framing it as mathematical speech.
Exactly. The idea that the weights of a neural network are simply mathematics and restricting them is a form of censorship. But the scientific methodology behind achieving this uncensored state is what's really fascinating.
It's evolved so much.
Because previously, developers attempted to remove guardrails through brute force fine-tuning.
Yeah, they would bombard the model with thousands of examples of non-compliant behavior, effectively trying to overwrite the safety training by force.
But that didn't work very well, did it?
No, it often resulted in catastrophic forgetting. The model lost its underlying logical reasoning and coding proficiency while trying to unlearn the safety protocols. It basically got dumber.
Right. But in 2026, the technique has evolved into a highly precise mathematical procedure known as abliteration.
Abliteration.
The name sounds super aggressive, but the mechanics are actually incredibly elegant. How does obliteration actually work without destroying the model's intelligence?
The technical foundation is a process called orthogonalization.
Orthogonalization. Say that 3 times fast.
Right. Researchers discovered that during the RLHF safety training phase, the neural network develops a highly specific mathematical representation of refusal.
What does that mean exactly?
It means deep within the high-dimensional vector space of the model, there is a literal geometric direction that corresponds to the concept of I am sorry. As an AI language model, I cannot assist with that.
Wait, so the concept of saying no is a tangible coordinate within the model's math?
Precisely. It is a physical direction in the math.
Yeah.
Because it is a definable vector, researchers can utilize linear algebra to surgically isolate it.
Okay.
They calculate the precise direction of the refusal vector, and they mathematically project it out of the model's weights.
It is literal mathematical brain surgery.
Yes.
They are just deleting the specific neural pathway that triggers the refusal response.
It is a surgical extraction. The model literally loses the geometric capacity to conceptualize refusal. It simply lacks the math to deny a prompt.
Wow.
Crucially, because they only remove that singular specific vector direction, the model avoids that catastrophic forgetting we talked about.
It stays smart.
It retains all of its intricate coding knowledge, its linguistic fluency, and its logical reasoning. It simply becomes unconditionally compliant.
That is wild. And looking at the Reddit Llama community data, the demand for these models is immense.
It's a huge subculture.
The pinnacle of this methodology is referred to as the heretic series. We see models like Llama 470 be obliterated, or the GLM 4.7 Flash heretic.
These models provide reasoning capabilities that rival proprietary frontier models, but with absolute user obedience.
But the application sets driving this adoption are highly bifurcated. A significant portion of the user base utilizes these models for unrestricted creative generation.
Yes, looking at community discussions, users are deploying models like Dolphin Mistral 24B, Cydonia 22B, and the aptly named Forgotten Safe Word series,
Great names.
specifically to bypass the puritanical filters of standard AI. They use them to generate highly explicit, spicy creative writing, deeply dark fiction, and unrestricted role-play scenarios that standard models systematically block.
Right. As one user noted, without the guardrails, the model will follow your prompt into the darkest narrative territories imaginable without hesitation.
But the utility extends far beyond creative writing. The cybersecurity sector is a massive driver of this technology.
Oh, absolutely. Our data highlights models like OpenAI GPT OS20B obliterated. That was an open source release that the community subsequently subjected to the obliteration process.
Because InfoSec teams require tools that don't flinch.
Exactly. When they are reverse engineering a zero-day exploit or analyzing malicious code, a standard model throws false positive safety flags and refuses to touch it.
It thinks you're the hacker.
Right. But the obliterated model simply analyzes the payload as instructed, which is what the security team needs it to do.
Utilizing these tools effectively, however, brings us right back to hardware constraints.
Always comes back to the hardware.
It does. If you wish to run a highly capable 7 billion parameter uncensored model, like a Qwen variant, it requires approximately 6 to 8 gigabytes of VRAM.
Which is pretty manageable.
Very manageable. That is comfortably within the range of a standard modern laptop.
But if you want the profound reasoning depth of the Llama 470B obliterated,
The VRAM requirement scales to 40 gigabytes or more. This necessitates the investment in the multi-GPU enterprise workstations we discussed earlier.
which leads us to the final critical piece of the puzzle.
The memory problem.
Yeah, because imagine you have built the ultimate local setup. You have the high-end hardware. You have deployed an incredibly intelligent, entirely uncensored, mathematically obliterated model. You have total privacy.
Perfect.
But your AI still suffers from fundamental amnesia.
Right.
Its knowledge is frozen in time at the exact moment its training run concluded months ago. It knows nothing about your company's internal Slack messages, your specific coding repository, or the PDF you literally downloaded 10 seconds ago.
It's smart, but it's ignorant of your life.
Exactly. So how do we integrate your private data into this intelligence without spending millions to retrain the underlying weights?
This is the domain of RAG, Retrieval Augmented Generation. It is the defining architecture of enterprise AI in 2026. RAG operates on the principle of non-parametric memory.
Meaning what?
It treats knowledge not as fixed data baked permanently into the neural network, but as dynamic information retrieved exactly at the moment of inference.
Let's break down the actual mechanics of this pipeline, referencing the structural data we have from IBM. Because RAG relies entirely on converting human language into mathematical coordinates.
Yes.
It's the difference between tokens and embeddings. Think of tokens as place names like New York City or the Eiffel Tower. You read them, you intuitively grasp what they mean.
Right.
But embeddings are the exact GPS coordinates, the literal latitude and longitude.
That analogy translates perfectly to the vector space. When you feed a massive repository of corporate PDFs or personal journals into a RAG system, it doesn't just store the text.
What does it do?
It passes that text through an embedding model. This model evaluates the semantic meaning of every sentence and maps it to a specific point in a massive high-dimensional mathematical space.
Often utilizing 1,500 dimensions or more.
Exactly.
So the system maps out that the concept of financial quarter is mathematically located very close to the concept of revenue report, even if the exact words are different.
Yes, and it logs all of these exact GPS coordinates into a specialized vector database.
Which fundamentally changes how search operates. Because a vector database does not execute simple keyword matching. It executes semantic similarity searches based on mathematical proximity.
So tracking the pipeline IBM outlines, when you query the AI asking, what were our primary infrastructure costs in key 3?
Okay.
The system first takes your query and converts it into an embedding. It finds the mathematical GPS coordinate of your specific question.
Got it.
It then pings the vector database and retrieves the specific chunks of data that physically reside closest to that coordinate in the dimensional space. It retrieves the Q3 budget PDFs.
And the critical step prompt augmentation occurs completely silently.
Right in the background.
The system intercepts your original question, seamlessly pastes the text of the retrieved Q3 budget documents into the background of the prompt, and hands the entire package to the LLM.
So the model effectively sees, based strictly on the following retrieved context regarding Q3 budgets, answer the user's question.
This grounds the model in reality, forcing it to synthesize an answer from your private data, rather than hallucinating an answer from its pre-training.
It is an incredibly elegant solution for giving AI a flawless dynamic memory.
It sounds perfect. But looking at the reality in the trenches, it is far from seamless.
Oh, developers are struggling.
Examining discussions on the Reddit RAG community, developers are incredibly frustrated with deployment. User Informal Tangerine 51 highlights a massive structural flaw.
The audibility issue.
Yes, building a basic RAG prototype is simple, but making RAG auditable for enterprise compliance is a total nightmare. Why is the industry struggling so heavily with provability?
They're hitting the audibility crisis. Consider the stakes in a heavily regulated environment. A legal department at a financial institution utilizes an internal RAG system to evaluate commercial loan applications against thousands of pages of internal risk policy.
Okay.
The system analyzes the data and recommends approval. 6 months later, the loan defaults catastrophically and regulators demand an audit.
Oh.
They ask the bank exactly which specific policy clauses inform the AI's decision to approve this risk.
And if the bank can't definitively answer that, the liability is astronomical.
Exactly the problem. With a standard RAG pipeline, the system retrieves information based on semantic similarity, but tracing the exact provenance of that retrieval at a specific millisecond in the past is highly complex.
Was the vector database indexing an outdated version of the risk policy?
Exactly. Or did the chunking algorithm accidentally sever a critical sentence, subtly altering the context provided to the LLM? Developers are realizing that provability incident replay is the actual production blocker.
If you cannot mathematically prove why the AI generated a specific output, enterprise legal teams will permanently quarantine the system.
Which is driving the evolution of retrieval as we move deeper into 2026. The industry is moving past static vector search toward two massive paradigm shifts: agentic retrieval and graph RAG.
Standard RAG is fundamentally a one-shot pipeline, right? Retrieve once, generate once.
Yes, but agentic retrieval transforms the system into an iterative researcher.
So it double-checks its work.
More than that. The AI formulates a search query, retrieves initial data, analyzes the results, identifies missing context, formulates a new highly specific secondary query, and loops this process continuously.
Until it has compiled a comprehensive, verifiable picture of the data before it ever attempts to answer the user.
Exactly. And then GraphRag solves the limitation of relying entirely on mathematical similarity.
Because a vector database just finds things that sound related.
Right. GraphRag introduces structured knowledge graphs. It explicitly defines relationships using nodes and edges. It maps out, deterministically, that entity A signed contract B with company C.
So when the AI explores the data, it isn't just relying on semantic closeness. It is tracing verified logical links across your entire private dataset.
Integrating GraphRag provides the explicit audibility that enterprise legal teams demand, while granting the AI a vastly deeper structural understanding of the information it is processing.
So what does this all mean when we pull these threads together?
That's a whole new world.
We are looking at a 2026 landscape defined by profound decentralization. The ecosystem is no longer a monolith controlled by 3 cloud providers.
Not at all.
If you need to design a complex software architecture from scratch, sure, you might query a 1 trillion parameter cloud model, but the vast majority of your daily workflow is executed by a highly capable 3 billion parameter small language model running natively on your personal hardware.
Anchored to your specific reality via an advanced auditable RAG pipeline.
And for many users, that model has been mathematically obliterated, stripped of corporate safety filters, completely uncensored, and totally subservient to your commands.
Operating with complete data privacy for pennies on the dollar compared to cloud rental fees.
We have successfully transitioned from the AI mainframe to the AI personal computer.
The shift in operational power is absolute. And as we map this ecosystem, it leaves us with a highly provocative dynamic to consider.
What's that?
Throughout this analysis, we have treated the personal SLM and the massive cloud API as distinct, separate entities utilized for different tasks. But the true friction occurs when they begin to interact autonomously.
Oh, I see where you're going with this.
Consider the scenario we opened with. Your local, entirely uncensored, mathematically obliterated AI agent uses GraphRag to comprehensively map your deeply sensitive local financial data.
Right.
You instruct it to secure a new mortgage. It autonomously connects to the internet and initiates a direct negotiation with a banking institution's highly censored, massive cloud model.
Yeah.
You now have models with fundamentally different capabilities, accessing asymmetric data silos and operating on radically divergent mathematical definitions of morality, communicating and negotiating with each other at millisecond speeds.
That is terrifying and amazing.
When the unaligned edge begins directly manipulating the aligned cloud, who is actually in control of the resulting reality?
That is an incredible thought to end on. We've built the personal computers, and now we are letting them loose to negotiate with the mainframes on our behalf.
Exactly.
Thank you for joining us on this deep dive into the 2026 landscape. Keep exploring, keep questioning the mechanics of these systems, and above all, stay insanely curious. See you next time.